Last time we learned about systems of equations. We learned that a system of equations is simply when we have two or more equations and they contain two or more variables. We said that we must have the same number of equations as we do variables. We saw how we could graph the equations and find the point of intersection. The point of intersection gave us a coordinate x and y, though that value for x and that value for y gave us the values that will make both equations true at the same time. We're going to look at another method today to solve systems of equations. What's really cool about this is you can solve a system of equations by using the graph or by using this method. Whichever method you use, you'll come up with the same solution. The method we're going to look at today is called substitution. You're actually very familiar with substitution because not long ago we studied function notation. And we said if f of x was 2x plus 5, in order to find f of 7, we simply plugged 7 in where we had x. That's known as substitution. We're taking away a variable and putting something in its place. Now let's take a look at our first example to see how we can apply this to systems of equations. In our first example, we have the equation 2x plus 3y equals 6. The second equation that we have is x equals 2y plus 5. The objective here is to eliminate one of our variables so that we have an equation that has a single variable in it. Here's how we go about that. We have 2x plus 3y equals 6. Down here we say that x is equal to 2y plus 5. Since x is equal to 2y plus 5, wherever I have an x up here, I can take that x out and put the 2y plus 5 in its place. So over here I had 2x. In place of the x, I put the 2y plus 5. Now I have an equation that has only one variable, and we know how to solve those equations. I'll now use the distributive property 4y plus 10 plus 3y equals 6. And I go through and solve the equation, and I find out that y equals negative 4 over 7. So I now have the y value. But remember, I need to have an x and a y, because I had both an x and a y in my original equations. It's actually easy to find the second value. X is 2y plus 5. Since I know what y is, I can substitute that in. 2y plus 5, 2 times negative 4 over 7 plus 5. That means x is 27 over 7. So the solution to this system is 27 over 7 and negative 4 over 7. Put this number into for x, that number in for y into both of these equations, and they will both be true. It's also interesting to point out that if you were to graph these two lines, they would intersect at those points on the graph. Example 2 is very similar. In example 2, we have the equation x plus y equals 1, and we have the equation y equals x minus 1. Well, it'd be nice if we could get down to just one equation with one variable, because those are very simple to solve. I can use this idea of substitution. Since y is x minus 1, I can go into the other equation, take out that y, and put the x plus 1 in its place. I'm simply substituting or plugging in the x minus 1 for y. X plus x is 2x minus 1 equals 1. 2x equals 2, so x equals 1. We now have the x value that will show where these two graphs would intersect. But remember, we need both an x and a y. Well, the y is actually quite simple to find because once again, y equals x minus 1. So y is x minus 1. We already know what x is, so we just plug it in. Y equals 1 minus 1, or 0. So the solution to this system is 1, 0. X equals 1, y equals 0. If you plug 1 in for x into both of these graphs, and 0 in for y into both of these graphs, both of them will be true at the same time. It's also important to note that once again, if you were to graph those two lines, they would intersect at the point 1, 0. Now I'd like for you to pause the video here and try the next example. Use the substitution method, then come on back, let's see how you did. Let's take a look and see how you did. On example 3, we have two equations, and our second equation is x equals negative y plus 6. Well, I can take out the x up here, substitute the negative y plus 6 in. So 2 times negative y plus 6 plus 3y equals 11. Use the distributive property, combine like terms and solve, we get y equals negative 1. Once again, we have to have both an x and a y value. So, since we know that y is negative 1, and x equals negative y plus 6, I can just plug in my x value to find out that x equals 7. So, I now know that the solution to this system is the point x equals 7, y equals negative 1. That's the point where the graphs would intersect, and those are the two numbers that I can plug into both of these original equations, and they'll be true at the same time. I'd like for you to try the next example. Please pause the video here, then come on back. Let's see how you did. Let's take a look. Example 4, we had once again our two equations. We have y as negative 4x minus 7, and so I can simply plug that into the other equation. Then I go through and solve. I get x equals negative 3. Don't forget to find the y value. Y equals 5. And so the solution is the point negative 3, 5. X equals negative 3. Y equals 5. Now sometimes when you work with these, you actually have to do a little bit of work in order to get going on it. Example 5 is a perfect illustration of that. Over here, 3x plus y equals 5. And 4x plus 5y equals 3. In order to use the substitution method, you need to get one of the variables alone in one of the equations. Now, to be totally honest with you, it doesn't matter if you get your x or your y alone. You can do whichever you choose. And to be totally honest again, you could do it with this equation or with this equation. As long as you pick one of them and get the x alone or the y alone. I happen to choose the top equation because I saw that the y had no coefficient and all I had to do was subtract 3x from both sides. I personally thought that was the easiest way to go, but there are many paths you could take in this example. Using my method here, if y is negative 3x plus 5, I just plug that into the other equation wherever I have a y. So here we go, 4x plus 5, this was the y, but we replaced it with negative 3x plus 5 equals 3. I solve and get x equals 2. Once I find x equals 2, then I can go ahead, find the value of y, and that gives me my solution, the ordered pair, 2, negative 1. Example 6 is the very same idea. You have two equations. You need to get one of them with the variable alone and perform a substitution. Please pause the video here, give that one a try, and let's see how you do. Let's take a look. In this equation, you could have done it several ways, so I actually didn't write out all the steps. There's 4 different ways you could have done this. So what I would have done, get one of the variables alone, substitute it into the other equation, you should end up with the points x equals 1, y equals negative 1/2. Once again, those are the values that when you plug them into both equations, both of them will be true at the same time. It's the point at which the graphs would intersect. Now, we saw last time that there's a couple of special cases. We have a case where the lines are parallel and they have no solution. We saw a case where the lines are right on top of each other. The two graphs are actually the same line, and so we had an infinite number of solutions. Since we're not looking at graphs this time, let's take a look and see what that would look like if we're using an algebraic method. In example 6, I decided I wanted to use a substitution. And so I picked one of the equations and got the variable by itself. In this case, I chose x. I plugged that into the other equation, 2 times 6 minus y plus 2y equals 15. Use the distributive property, and you have 12 minus 2y plus 2y equals 15. Now negative 2y and positive 2y cancel each other out. I'm left with 12 equals 15. Notice my variables are gone. Whenever my variables are completely gone, I have one of my special cases. Now, in this case, what I'm left with makes no sense at all. 12 equals 15. That's gibberish. Because it makes no sense, there is no solution. These lines are actually parallel. And if you were to get both of them into slope-intercept form, you would see that they have the same slope. Our final example we'll take a look at is an example in which we have an infinite number of solutions. I began with my two equations and I decided to use substitution. So what I did is I got the variable alone in one of them, in this case x equals negative 2y plus 4, and I plugged it into the other one, and I solved. Once again, my variables fell out. I have no variables left, but notice this time what I'm left with makes total sense. 16 equals 16. If you get something that makes sense, that's good news. Because it makes sense, what we really have are an infinite number of solutions. These two graphs are actually the same exact line. And if you were to get them both into the same format, you would see that they're actually the same line. So now we have two different ways we can work with solving systems of equations. They're actually the same thing, just two different processes in order to find the values that make both of the equations true at the same time. The first option is graphing. The second option is using the substitution method.